Okay, good morning, everybody. I hope you guys are doing well. Today we're going to work on some functions as power series, but before we do that, let's go to the browser. Let's double check again in this browser. Okay, so I want to remind people that I did last Thursday, I did put up your examples on power series. I believe it was Thursday or Friday morning. I can't remember. Um, Examples in power series, and we're looking at intervals of convergence. And looks like 22 of you guys actually did view that, which is good. And so, yeah, I guess May 22nd, whatever that was, 4 days ago. So, if we look at our schedule, we see what's coming up. And today is the 22nd. And so we got about 3 more days, and you get your June 1st test 4, and the June 2nd is the very next day. So I'm going to put up for you guys some study guides as soon as I can, so that you guys have some information prior to that. So we'll get some study guides for you guys. Okay. What else do I want to say? Yeah, I guess that's just coming up. So, all right. Well, okay, that's on our horizon. So we'll have more information to come as the days get closer. So I'll get the study guides up for you guys here. And then here we have the power series representation here with functions. Now, this is all based on one power series. So I want you guys to recall this particular power series. The sum n equals 0 to infinity x to the n, which is x to the 0 plus x to the first power, x to the second power, and that goes on forever. But we know this is 1 plus x squared, and okay. Now remember, an important idea is this. If the absolute value of x is less than 1, then we have convergence. And we know where that converges to. That will converge to 1 over 1 minus x. Okay, so we actually have this geometric series. Here's A, here's R. This is the R portion. So we get convergence to this function. Now, here's what this means in summary. So n is 0 to infinity, x to the n, 1 minus x. This is the function that they're talking about. And over here, this is the power series representation. So we have a power series representation. The domain of that function is all values between -1 and +1. And these are the values we get convergence. Okay. So what we're going to use today is this function. So let me rewrite this so that you can see the context. We have 1 over 1 minus x. This function is the sum 0 to infinity, simply x to the n. So this one little function is the basis of what we want to talk about, which is to represent a function. Here's that function f of x as a power series. So there's some various things that we can do. For example, I can look at this function here and say if you had 1 over something very simple, 1 plus x. We want to represent this function as a power series. And what you do here is we know that minus a minus x is plus x. So you're going to use this power series representation here. And you might say, well, how do we use that? Well, I'm going to rewrite this as 1 over 1 minus a minus x. And I'm going to replace this here. This is what's really happening here. This minus x here gets placed in, or we replace the x here with that minus x. So this portion here is really minus x because that portion is what we're talking about. And really, if you want to think about it, what you're really using is this idea. That we could describe this situation as x to the nth power. And again, you know that that's going to be 1 plus triangle to the second power and so on, where this is just a placeholder. And that's actually what you're trying to use, that particular placeholder. So you're going to replace this, and then you say, okay, well, what does that give me? The series then will look like negative x to the nth power, where n goes to 0 to infinity, 1 over 1 plus x. And I just use some algebra here, meaning properties of exponents. Okay, because there's a negative 1 here, and we simply distribute the power. And you're going to end up with a negative 1 to the nth power. Oops, we forgot our series. N is 0. We end up with negative 1 to the nth power, x to the nth power. So here's a power series representation of a new function. And it's an alternating series. So if you just looked at some of the terms, you can say, okay, that's going to be 1 minus now x plus x squared minus x cubed. It's an alternating series. And again, you talk about the interval of convergence, where the absolute value, in this case here, this is the r value. So the absolute value of negative x, which is the same as positive x, we get the same domain or interval of convergence here. So ladies and gentlemen, this is writing a new function in terms of a power series here. So here's the power series, and that's what we're going to look at today. And it's a very interesting concept. The key, though, is right up in here. Maybe if I can, here's your key. That's what we're using today. So we got a new function, and that's what they're going to ask us to do. And so if we look at some various examples of this, and your book has some nice kind of examples, I guess your book starts with something like, how would you handle writing 1 over, I might do a little something here. How about this? 1 over, all right, let's do this. I think they say 1 over 2 plus x maybe. And we have to do a power series expansion for this. Another example. So remember here, the only tool you have to use so far is this representation. And we have to write that particular function in this format. And here's how you start to do that. You might want to consider this term here, this 2. That needs to be a 1. So what we're going to do here is we're going to factor out the 2. And you say, how do you factor out the 2? Well, you're going to have 2 now times 1 plus x over 2. So make that 2 a 1. This is what we just did, and we factored out the 2. I'm going to write that down. Factor out that leading term. So notice if I multiply and distribute, I get the same 2 plus x. Okay. So this is now 1/2 times 1 over 1 plus this x over 2. And so we're getting closer. It kind of looks like 1 minus that triangle. And it'll be even closer if I focus down here and write this portion as 1 minus a minus x over 2. So altogether, 1/2, 1 over 1 minus that minus x over 2. And now, if you take a closer look, we can see we're in this particular format, so that what's in the triangle here is that minus x over 2. Okay, so you say, well, what do I do with that portion? Well, replace it with the summation minus x over 2 to the nth power, where n is 0 to infinity. Because remember, this is what exactly this power series is. If we just use that as our base to the nth power here, that's the power series representation. But we have to do a little bit of algebra here. Okay, so there's some algebra to perform. And you say 0, infinity. Now we're going to do the same kind of algebra here. I'm just going to look at this as, -1 times x over 2, and that's going to be to the nth power. So you're going to end up with -1 to the n, x to the n over 2 to the n by properties of exponents. Now, remember, for properties of summation here, we have a constant. This is a constant times a sum. So what that means is I can put my constant inside the summation. So this is 1/2 times -1 to the n, x to the n over 2 to the n. Now, by some algebra or arithmetic, we have -1 to the n, x to the n over 2 to the n plus 1 now. Because we're looking at down here multiplying these two, because we're multiplying fractions, and you multiply to the denominators. So here's another power series representation. And this was actually 2 plus x. Yeah, okay. So here's my function, 1 over 2 plus x. And we want to note, again, the interval of convergence. If I go back and say to you, this is the r value, that minus x over 2, right? This is what we're looking for. There it is. Okay. So the absolute value now of minus x over 2 is the absolute value of, well, it's going to be absolute value of minus x, so the absolute value of 2, which is the absolute value of x over 2, and that has to be smaller than 1 for convergence, which means that the absolute value of x has to be smaller than 2, or -2 less than x less than 2. We have this interval of convergence, or the domain of our function. So we're looking at this power series expansion for these functions. And then they might say, okay, what if they did something to you like this? And they will. They might say, write, for example, x squared over 2 plus x. They want the power series expansion for something like this. And you're going to use what you know and some algebra. So you might say, I can write this as a product of 1 over 2 plus x, right? And you just actually wrote the power series expansion for right over here, 1 over 2 plus x. And that looks like this. This is replaced with the sum, negative 1 to the n, x to the n over 2n plus 1. And that's n is 0 to infinity. So by knowledge of the power series expansion for 1 over 2 plus x in the prior example, we replace that with that power series. And so you say, does that give you now x squared times that sum, negative 1 to the n, x to the n, 2n plus 1, where n starts at 0 to infinity. And it does. Right? But again, what will happen is I can now use properties of summation here. I can multiply here this x squared. I can put this in by the distributive property, because this is a product times a sum. So this becomes the summation from 0 to infinity, negative 1 to the n, x to the second power times x to the n over 2n plus 1. And by algebra, properties of exponents again, we can actually write this as the sum now, n is 0 to infinity, negative 1 to the n, x to the n plus 2 over 2n plus 1. And that was x squared over 2 plus x. And so you can actually say, here you go, here's an answer, here's a power series expansion. You can say you're done. However, you might look in back of the book, and in back of the book, they do a few things. In back of the book, you might say, I see an x to the n right here. This is x to the n. And I don't see the n plus 2. And then they're going to change where you start here. And here's what you can see in back of the book, right? So I'm not doing the exact example in the book. I changed it a little bit. So if you compare that, you can say, oh, he did something a little different. So here's what I want to remark. Here's what you can do. We can say this portion up here, you're going to let I be n plus 2, right? And then if you subtract 2 from both sides, you get I minus 2 is n. So I'm going to change the index. Here's a summation, negative 1. Now this is x to the I over 2. We have to find the new power. So I'm going to replace this n plus 2 with I. That's why you see here an I. We have I here going to start somewhere. But the question becomes, what happens to n plus 1? Well, since I have here that I minus 2 is n, if I add 1 to both sides, I get I minus 1 is n plus 1. So this becomes I minus 1 now. So I'm going to substitute n plus 1 down here with I minus 1. And let me write that I a little better. And so you get I minus 1, and that was substituted. But similarly, you can say, but I have an nth power here. Okay. Well, you can replace that with, down here, the I minus 2. And then you can say, well, where do I start now? Well, you're going to start with I is actually 2 to infinity. And you say, why would I start with I as 2? Well, go back over here. Go back to what you let I be. When you plugged in what you started with, n is 0 over here. That makes I being 2. So just by letting I being that n minus 2 originally up here, you get a nice power series representation in terms of this x variable having the ith power. And that actually is what you see sometimes in books. You may not see n plus 2 here. You can. That's fine. If you wrote it that way, it wouldn't be wrong. But you might see a variable there that's, in fact, not even necessarily I. You can see this as well. This is another answer that you can write, and that's perfectly fine. But I'm going to say to you, they changed the variable back to n. So if you're looking back at the book and you see n starts with 2 to infinity, -1 to the n minus 2, x to the n over 2 n minus 1 for this x squared over 2 plus x, right? You might see the power series expansion look like this, and it may confuse you. Okay, so it confuses some students sometimes when they say, okay, I did the work you showed, Mr. Judge, way back here. If we get rid of all the colors, I did this work, and it starts with 0, and it looks like this. And my power for x is n plus 2. And then I'm looking back at the book, and it has x to the n. I don't know what I did wrong. And then this is n minus 1, n minus 2. In fact, they might even change this, and you start with n is 2. And you might say, well, I'm looking back at the book, and let's think about this. If n is 2, 2 minus 2 is 0. So I get -1 to the 0, which is 1. Because that's I can say this. They'll replace this n minus 2 with an n because it differs by 2, and -1 to the second power is exactly the same as -1 to the 0 power. They're both +1. So they'll even modify that alternating mechanism, and they'll write this in a very simpler kind of way, a power series in this form. But it's okay. So when you're looking back at the book and you might say, wow, I did all that work and this is what I get for the power series. Yeah, they're just writing it in a little bit easier way. But this is what they're going to expect you to do today with some of these power series. And so I changed this slightly for you guys. And again, you might say, well, what's the interval of convergence? Well, since you used this representation here, it's the same, right? It's from -2 to +2. So your interval of convergence will still be from -2 to +2. And anyway, so that's kind of a little bit work with algebra. It's all based on that, replacing this portion here with I. But they're all equivalent. They're all the same power series representation. Okay, so that's kind of some fundamentals of how to work with some of these. I could do a few more, but I might save them for some examples, depending on how far we get. But what I want to give you guys is a very, very powerful theorem that we're going to use to create other power series representations. So let's go with some assumptions. So here's a theorem, and I'll put it way down here. I'm going to write down the general power series. The power series that looks like this. N is 0 to infinity, c to the n, x minus a to the n. Now remember, this is c naught. If I start with the expansion, c1, x minus a to the first power plus C2 x minus a to the second power, and that goes on forever. So you start with the power series expansion in general, about a, not about 0, about a. What we know here is that it has an interval of convergence for the absolute value of x minus a less than r. And yes, by definition, that's a minus r, a plus r. So we went over this, in the past. So here's what they want you to know. This is differentiable and integrable. So we could differentiate and integrate the power series expansion. So remember, this equals some function. So some function is represented this way. Here's that same function, just expanded. So here's the theorem. F prime x is d dx of the summation n is 0 to infinity Cn x minus a to the n. Now, derivative of a sum is sum of derivatives. So I can put my derivative inside the summation. Now, furthermore, I can say to you, we'll have Cn d dx. I pull out the constant here. Pull out my constant. Remember, Cn is a constant. I can pull that out by properties of derivatives. And so now I'm right here. And we're going to have to be careful here because notice what's going to happen here, right? Summation. N is 0 to infinity. I have that Cn. Now, when I differentiate, and I'll change colors here, by power rule, this is n x minus a to the n minus 1 power. So we're right here differentiating. And altogether, you might say, that looks like we just put the n before the constant, n Cn x minus a to the n minus 1 power. Now, be very careful here because what happens now, since my index, the theorem says this. When you differentiate, you're going to start with 1. N Cn x minus a to the n minus 1 power. And you might say, well, how come you went from n is 0 to n is 1? Well, because notice, if you start to expand and you replace this n with 0 here, right? And then this is C0, and then this is 0. Here you get 0 times a constant, and that's 0. So that term is zeroed out. So this whole thing here is 0 when n is 0, so they start with 1 instead. Now, that's only part of the story here. Remember, this here was represented as f prime x. And I want you guys to note something here. Yeah. Well, they're going to write it as f prime x. We're going to have that there. I want you to notice something here. Here's kind of a fact, and they just mentioned this in your book, and they don't prove it to you. This will always have the same radius of convergence. And I'll put this in red, but not necessarily. You may not have the same interval of convergence. So that's an important detail. Nevertheless, we have a way to perform a power series expansion for a derivative for other functions. So we're going to start again, and your book starts with that. If you recall again, the basis of what we're doing. 1 minus x is represented this way as a power series. So if I differentiate now both sides, the left side, we obtain the following. I guess we can do it a couple of ways. I think I'm going to look at this way. I'm going to change my color here. I'm going to use the following. This is 1 minus x to the negative 1. So if I differentiate the left side here, I'll get negative 1 times 1 minus x to the negative 2. By chain rule, I have to differentiate 1 minus x. This is by chain rule, and I get negative 1. So that these constants here cancel. And what you end up with now is 1 over 1 minus x squared. So that's the derivative of the left side here. And if I look at properties on the right side, this is good. This is replaced with the sum of d dx, x to the n is 0. We know that when we differentiate here, this portion is nx to the n minus 1, but altogether, change the index. I get the sum, n is 1, and x to the n minus 1 on the right side. And let's keep that, well, I'm going to keep it the way it is. Okay. So don't forget, this is the left side of the equation, and this is the right side of the equation. So my power series expansion now for a new function is n is 1 to infinity n x to the n minus 1. And you might say, but Mr. Judge, I'm looking in the book, and it gives me a different expansion. In the book, they say n is 0 to infinity, and they have this m plus 1 x to the n. And you might say, how did they go from what you just showed me to what they have in the book? Well, they did exactly what I described earlier. They're going to call this I here. So you're going to say, let I be n minus 1. This is called really a change of your indices. Change the index letter. So if I is n minus 1, from here, we get x to the I now. But using some algebra, right? If you solve that for n, you get I plus 1 is n. So over here now, because you have an n, they replace that with I plus 1 here. And then you say, okay, but what about the starting point? Well, you start here with n is 1. So if n is 1, I becomes 1 minus 1, or I becomes 0. So now you say this is I is 0. So you can say that the power series representation here of 1 over 1 minus x to the second power can be described as I goes from 0 to infinity, I plus 1, x to the I. You can keep it this way. However, if you look at the book solution, what did they do? They changed your indices back to the letter n. So this is what you can do, since it doesn't really matter if the letter is I, K, J, or N. They're all kind of interchangeable at this point. Don't try to interchange them up here, when you start working with that. But once you get a representation here, it's okay to go back and say, you know what, I'm going to call you N. And that's what the book did. So the book says, okay, instead of I, let's change you back to the N. And now you get the consistent version over here for what the book says is your representation. But, these are the little details that you need to know as you do some of these questions that don't drive you crazy, because you get a very different representation. What they did was they always do this. They go back to a simpler version of that power. And it doesn't even matter. You don't have to do this. You could use this expansion. That's a power series expansion. That's perfectly fine too. But they go back to this kind of representation that's a little bit fundamental. And that's why you see in some of the solutions, you have to be very careful. For me, the tip-off is looking at the index down here. Where does it start? And that's why you have n plus 1, x to the n, starts at 0. And here is the power series expansion for taking the derivative of that first function that we looked at in the beginning. So that's the derivation of where this formula comes from. For this new function. And the interval of convergence may not be the same. You'll have to check it. But, you check it by the processes that you've had before. It'll definitely have the same radius of convergence. So your book just gives you that information. The radius of convergence of differential series is the same as the radius of convergence for the original series. You just may have a different interval, but you have to double check that. And I do want to do another the second part of this is the integration part. So go back and say, okay, we know we can differentiate. This is the representation. The second part is we can integrate. So if we take this function and we have the power series representation, in general, we're now going to do the following. Yeah, let's keep that in purple. We're going to integrate both sides with respect to x, so that we get the integral here of, integral of fx dx. Using properties of integration, that the integral of a sum is sum of integrals, we can put the integration symbol inside your summation, Cn, x minus a to the n dx. We can pull out the constant like we did before. Cn, x minus a to the n dx. And now, just like before, we are right here. Maybe we'll stick with that purple. In other words, we simply have to integrate here. And you use power rule here. And by power rule, you can say we get the following. X minus a to the n plus 1 over n plus 1. And then don't forget you have this constant c. So let's kind of put everything here together here. You got the summation, n is 0, infinity, Cn, we don't have that integral sign. We already integrated. And we get the following. X minus a, n plus 1 over the n plus 1. And you say, well, what about this c here? There's a c there. And so if you're looking back at the book, or you say, okay, what does this theorem say? here's the theorem. They're going to put your constant outside, and I could explain why. And then they have Cn x minus a to the n plus 1 over n plus 1. And that's the integral of fx dx. So we have a very important way or another method here to actually integrate. So remember, in generally, just to kind of get a little bit off topic here, since that's always fun, remember, you can't always integrate functions. Functions aren't always integrable. However, we can actually have a way to integrate functions by looking at the power series representation. And that's why this is a very powerful concept for you guys in Calculus 2, that it gives you a way to integrate. You just have to integrate the power series. And if you have limits, you can actually approximate answers by looking at, not the infinite sum, by only, partial sums. So this is the formula that they give you for this. And I said I was going to explain. Remember why they pulled the constant out. Really, it's a consequence of doing some algebra, distributing. That remember, Cn for all n is 0, 1, 2, 3, forever, times a constant is another constant. So they just decide to put this. It's a different constant, but we've been through that discussion all throughout the course. But that's why you see in this theorem for the second part for the integration is they just put a constant outside, and then they integrate the power series variable. And so this is the second part of that theorem. And again, it has the same radius of convergence, but not necessarily the same interval. So same radius of convergence, but not the same interval. Of convergence. And your book has an outstanding example. And this is kind of where we're headed. So they take, here's what your book takes. Since I'm going to say, recall, I think we did this, or maybe we didn't, but it's okay. We'll do it now. If I know the power series expansion of 1 over 1 plus x squared, well, that's going to be written as let's find this expansion. 1 minus x squared, which is going to be the series or the sum of n is 0 to infinity of negative x squared to the nth power here, right? Because this is going to be in that triangle. That's what we highlighted in gray earlier. And the power series expansion here is going to be by properties of exponents. Right, we're going to distribute that power of n here to a negative 1 and to the 2. So that makes it now 2n and n. So it's alternating. And this is the expansion. So 1 over 1 plus x squared looks like this. And if you looked at the details, you might say, oh, is that going to be 1 minus now x squared plus x to the 4th minus x to the 6th and so on, and it's alternating? Yes. We can find that interval of convergence. We just take the absolute value of that minus x squared, which is the absolute value of x squared, which is x squared, and is less than 1 because this is positive. And x squared being less than 1 by beginning algebra, we know is 1 is less than x, which is less than 1. Sorry, intermediate algebra. You could do sign analysis if you want, right? That's an inequality, sign analysis. So here's my interval of convergence. Now, this is an important fact. So as a separate problem, I have a function represented as a power series. But what I want to do is show you guys the following. I'm going to prove to you here we have another power series. Here's a fact. That the inverse tangent function can be written as the sum 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. And how you actually do that is by integrating this particular power series, right? So here's an example of the integration property to prove this fact. So if I said to you, okay, we're going to prove this expansion, we know that when we integrate the function 1 plus x squared dx, that's the integral of the power series expansion. Here we go. Sum n is 0 to infinity, negative 1 to the n x to the 2n. And dx, sorry. So in some ways, I guess you can say there's a bracket there. Now, on the left side, we know, well, simply that's inverse tangent. And that's going to equal to c, the constant, plus, now, maybe you guys want that purple back. I think I do. I like to save very important facts for the color red. So we get c plus, the integral of a sum is sum of the integrals. Right? Integral of sum of integrals. And I can put the integral sign here, negative 1 to the n, x to the 2n, and that's dx. C plus the sum, n is 0 to infinity, pull out my constant, negative 1 to the n, and I simply integrate x to the 2n dx. So we're really right here. All of this by properties of summation and properties of integrals. Well, this is going to be x to the 2n plus 1 over 2n plus 1 by power rule. And I guess that's where the red comes in. X to the 2n plus 1 over this 2n plus 1. And you get c plus the summation, n is 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. And you can say, here is my power series expansion for the inverse tangent. However, you might say, well, what about this c here, right? Well, you can get rid of that c, or I should say not get rid of it. That's not the proper way to say this. I want you guys to note that what you can do is let x be any value. Here we're going to let x be 0. And if x is 0, we replace the 0 here wherever there's an x. Notice what happens. We know that the inverse tangent of 0 is actually 0. So this portion becomes 0 here. And in fact, if your variable x is 0, any powers makes it 0 as well. So this portion also becomes 0. So what we have here is that 0 is actually c plus 0, or the value of c, the constant, is 0. So that eliminates the constant. So you end up with the inverse tangent being the summation, n is 0 to infinity, negative 1 to the n, x to the 2n plus 1, in fact, over 2n plus 1. And this is exactly the statement they want you to know. So it's an illustration of how integration can actually help you with some of these power series expansions. You create another expansion, and this time for the inverse tangent function. So, we're generating ways to actually write functions that we know as power series. And that's the essence of this section, which is 12.9, called representation of functions as power series. Okay. Now we could do a few more. We may do a few more. I mean, I can actually take a look, and I know your book does it, but it looks at the function, the power series expansion that we started with. If we said we know that, recall this expansion, right? This is going to be summation n is 0 to infinity. I believe that's -1 to the n, x to the n. It's alternating, and it converges again for the absolute value of x being less than 1. So we've seen this already. Another example of integration, I believe. So if we integrate dx, on the left side, we'll get natural log 1 plus x, because we have to do u sub here, right? U is 1 plus x, we integrate, okay. So the natural log of 1 plus x. So the integral of a sum is sum of integrals. And then we can say, pull out the constant, and we just have to integrate here. And this portion, x to the n plus 1 over n plus 1. Sum n is 0 to infinity, -1 to the n, x to the n plus 1 over n plus 1. And don't forget, there's a constant c. So here's my natural log 1 plus x. Let's not forget about the constant. So again, if you wanted, I guess we can say if we let x be 0, right? 0, 0. On the left side, we get natural log of 1 is the summation. Sorry. Natural log of 1, this portion here, goes to 0 because x is 0 right here. And what happens now is we get here, natural log of 1 is 0 plus c. Well, natural log of 1 is 0. So c here is 0. So let's write this down. Natural log 1 plus x, n is 0 to infinity, -1 to the n, x to the n plus 1 over this n plus 1. Now, okay, let's double check. So we have a question, 1 minus x or 1 plus x? I did 1 plus x actually in this example. Let's double check to see what your book does. So let's see, I did a 1 plus x. Yeah, it's a good observation. Your book did a 1 minus x there for you. So you could compare, right? You can compare what your book did. Your book did a 1 minus x. I did a 1 plus x. I essentially got rid of that negative sign. So I did it slightly different. So you guys can compare and contrast. So double check my work for the natural log of 1 plus x. My u sub didn't involve a negative 1. And your book has a slightly different version. So that's good. So compare and contrast what this representation is. And let's double check here. Here's what you can also notice, by the way. I can adjust this. Right? You might say, can I do that trick that sometimes is done where you let I be n plus 1? If I is n plus 1, you know that the power series looks like negative 1 to the n, x to the I. Let's get rid of that n. Over I. And you say, why not n? Because if I solve for n, that's I minus 1 is n. So I replace this n with I minus 1. And then you said, but we start with n is 0. So if we let n be 0, this starts with I being 1 to infinity. So at this point, you might say we can write this as the sum I is 1 to infinity, negative 1 to the n. Let's change the index. Let's write that down. Right? We can replace I with n. And so you end up with negative 1 to the n minus 1, x to the n over n, where now I starts with 1. And let's be consistent here. 1 to infinity. So you can see this version as well. And that's a little different. So I did natural log 1 plus x. And don't forget n. So all they did was change the indices back to what it should be. And anyway, this is a version here as well. So let me double check here. Yeah. Okay. So I want you guys to know, you might say, well, what's your interval of convergence back here? Well, we already talked about that. That's here. Negative 1 to positive 1. So we got negative 1 less than x less than positive 1. So you go back to the original there. Actually, I should say it's going to have the same radius of convergence, not necessarily the same interval, but you could double check that by the ratio test. So you could use the ratio test to get the actual interval. I believe it's going to be, so you guys know, I believe it's going to be these values here. So this is an explanation of some of these here. Anyway, how about if we do something like this? Yeah, we can do that. Okay, so here's some power series expansion kind of questions that you can see. And now I'm going to give you guys another one here. Give you an example just to kind of show you what they're going to start you off with trying to find power series expansions here. I'm going to do, how about if I do something like this? They're going to say, here's a function. X over 3x plus 1. Now, I'm completely making this up right now. I'm just looking at your book, trying to start with a function, and they're going to say, write the power series expansion. Start to look at some of these examples. Now, how you start, again, is that you write this fraction as a product. And this portion here, remember the tool that you have to use is that this expansion is 1 over 1 minus that triangle for the absolute value being smaller than 1. This is what you're going to use. So the idea now is to use algebra down here. That this can be written down here as 1 plus 3x. So if we have x here, 1 over 1 plus 3x, you want to write this portion now as 1 minus a minus 3x. And there it is. You're going to use this for your triangle. So we're going to write this whole portion as 1 minus a minus 3x. So x, power series expansion, summation, n is 0 to infinity, negative 3x to the nth power here. Okay, so you're going to replace this down here. This is what's in the triangle. So we're using this idea. That always goes here. And just raise it to a power, nth power. And of course, you say that assumes the absolute value of that minus 3x needs to be smaller than 1. And so by algebra here, this is negative 3 to the n, x to the n. And at this point, I can distribute. I can put the x back in. So this is x, negative 3 to the n, x to the n. You say, what are you talking about? Yes. By the distributive property, x times that sum, the x is now here. And again, by properties of exponents, we get n equals 0 to infinity, negative 3 to the nth power, x to the n plus 1. Now, you're kind of done, I should say. In some ways, this is over. So what's the original function? X over 3x plus 1? So you did a power series expansion here. And you're done. However, you may look in back of the book, and you might see again a couple of things here. You're going to see that they write this as this portion here. This can be replaced with negative n 3 to the n. So that you also can see negative 1 to the n, 3 to the n, x to the n plus 1, n goes to 0 to infinity. So you can see this expansion as well. It's not a problem. And then you might say, but they did that thing where they changed the index. And you said they're going to let I be n plus 1, which means n becomes I minus 1 by some algebra. So you can see here that the series is negative 1 to the I minus 1, 3 to the I minus 1, x to the I. And when they say n here is 0, n is 0, plug in a 0 here. So that I starts really with 1 here. So you can see it this way, but then you might say, what did they do again? They change the index from I to n. So I want to cover the idea that if you look in back of the book and you did this, you say, I see something kind of very different. Yeah, because they want to just describe this in terms of x to the n. That's what they chose to do. And that's a power series representation of that original function x over 3x plus 1. So I wanted to get through today for you guys some power series expansions. And it looks like I guess I will do a little bit later here today some extra examples on working with this representing functions as power series. And I will also get up for you guys some study guides as soon as possible for your test 4 and final. But let's also give you the last thing. Remember this interval of convergence here. Just use properties of absolute value. And that's 3, absolute value of x less than 1, or the absolute value of x is less than 1/3. So this is good for negative 1/3 less than x less than positive 1/3. That's your interval of convergence. So if you said, how can I look at some questions on this? Well, that's 12.9. I'm looking at some that look like the following. How about, we're going to try to do 1 to 18 all. And I'll do some more for you guys. Like I said, I'll do some more examples for you. And there you guys go. So if you have any questions or issues at this point with some of this stuff or what's going on, I'm going to say, see me during office hours. I'm going to send you guys a whole new link this week so that you can just click in Zoom and I'll be right there. Okay? So I hope you guys enjoyed this. Have a good day. Take care. And if there's other questions or issues, come see me in office hours and we'll see what we can do. But we're writing functions as power series. Now, these functions can be integrated, differentiated, described, and you actually see this as the basis of some topics in future courses. So you do want to get to the power series expansions and how to write functions this way. So take care. We'll see you guys tomorrow or a little later, and keep working hard. And thank you so much for your help and your assistance. Okay, I do appreciate all of you guys' help and assistance with some of these questions. So Alexis, thank you too, and we'll see you guys tomorrow.